the reversible polytropic process for an ideal gas. When a gas undergoes a reversible process in which there is heat transfer, the process frequently takes place in such a manner that a plot of log P versus log V is a straight line as shown in this picture. For such a process that there is heat transfer, the log P for example equals to n log V. For such a process, this PBL equals to constant. A process having this relation between pressure and volume is called polytropic process. An example is the expansion of combustion gases. In the cylinder of a water cooling reciprocating engine. If the pressure and volume are measured during the expansion, a stroke of a polytropic process, as may be done with an engine indicator and the logarithm of the pressure and volume rate plotted, the result would be similar to the straight line in this picture. From this figure we can write this relation D log P on D log V or DLNP on DLNV equals to minus N. So we can obtain this relation. DLNP plus N DLNV. If N is a constant, this equation can be integrated to give the following relation. PVN P1V1N equals to P second V second N. From this equation, the following relation can be written for a polytropic process. We have P second on P1 for a polytropic process from this relation. And also we have similar relation for isentropic process where the entropy change is 0. On those equations we have K instead of A. K is Cp on Cv. For a control mass consisting of ideal gas, the work done at the moving boundary during a reversible polytropic process can be derived as this W, a path function, P dV and PVN equals to constant. With integration from constant integration dV on Vn P second V second P1 V1 on T second T1 for an ideal gas. And if n equals to 1, there is also another relation that we derived also this equation in previous chapters. For PVN we have constant dV on V constant L and V 2V1 constant is PV V1 V1 for example. The polytropic process for various values of n are shown in this picture. PV and TS diagrams of various polytropic processes. PV for n equals to -1, n equals to 1, T constant, and n equals to K for S constant, isentropic. There is also a TS diagrams for a process n equals to 1, T constant, and for S, P constant is also there, and n equals to K isentropic S constant. So we can write these conditions. Isobaric process, pressure constant, P n equals to 0 and P constant. For isothermal process, n equals to 1, T equals to constant. And for is the isentropic process, n equals to K and S equals to constant. Isochoric process, n equals to infinity and V equals to constant. The most used process in thermodynamics is two processes. The reversible isothermal process for an ideal gas, reversible isothermal process for an ideal gas is of particular interest in this process. PV equals to constant P1 V1 P2 V2. The work done at the boundary of a simple compressible mass during a reversible isothermal process can be found by integrating the equations the integration is obtained before and or we can write because there is no change in internal energy or enthalpy, there is no change in internal energy and enthalpy in isothermal process. Du equals to T dt should of equals to 0. The transfer is equal to the work, neglecting change in the kinetic energy and potential energy. The transfer equals to the delta W. And also we have delta Q, which was du plus dv equals to dp d. We have for integration Q T ds or equals to p dv. For a isobaric process, the relation can be obtained as this is equals to also the next section is about entropy change of a control mass during an irreversible process.